Hello everyone. We learned a couple of things. We learned fundamentals of linear regression in our previous videos. For example, we learned that our dependent variable y will be continuous data. We learned the different types of data: continuous, discrete, quantitative, qualitative. And then we saw that we will use some historical data to build some predictive model. And we solved the linear equation and linear regression equation. What are the notations, what are the y-intercept bias, what is coefficient, and then we saw what is error. Simply, error is the difference between the actual and the predicted value. And then we saw the types of linear regression, simple and multiple. If we have one independent variable, then this is simple linear regression model. If we have more than one independent variables, then this is multiple linear regression model. Now let's see how to find the fittest model. Let's look at this graph. This is x, our independent variable. This is y, our dependent variable. And this is our data distribution. For this data distribution, we can build different linear models. As you see, all of them linear models. But of course, they are not the same. Initiatively, you can see that this one is the best one, because it represents the data distribution better than other ones. For example, this one, the first one, may be good for these specific points, but we can easily see that the total error will be higher in this graph, also in this graph and this graph. But this one will minimize the total error. So the idea is find the model which has the minimum total error. But how? Let's look at. Okay, remember our equation. This is our y-intercept, this is our coefficient. We have some x as an independent variable, and we will try to find the best value for this coefficient and y-intercept to minimize this error. This will give us the predicted value. This is the actual value. So we want to minimize this error. In other words, we can say that we want to find the best weights, best values for this part to make it closer to the actual value. Okay, the question is, how can we determine the error? So we will use loss functions here. And when you look at the definition of loss functions, you can see that they are for calculating the difference between the predicted output and the actual output, so the error. You can see also there is a cost function, and the cost function is very similar to the loss function, but basically loss function is for single values, but the cost function is for the entire data set. As you see in the definition, not only for single predicted and actual difference, for the entire training data set. Okay, we will use loss functions, and actually there are different loss functions, and according to your problem, according to the requirements, you can select one of them. And these are some of the loss functions: mean squared error, mean absolute error, root mean squared error. These are the most popular ones: mean absolute percentage, Huber loss, log cost, quantile. Of course, I will not show all of them, I will not give the details, and also you don't need at the moment, but I will try to show what is the most important factor in the loss functions. To make it clear, let's look at our flowchart. Until now, we saw some actually statistical techniques, some mathematical expressions. Now let's look at the flowchart of the linear regression as a machine learning model. Okay, at the beginning, we will start and we will initialize the weights randomly. Remember, we want to find the best values for y-intercept and the coefficients. If it is simple linear regression model, we will have one independent variable. That means we will have one coefficient. But if we have, let's say, 3 independent variables, then we will have 3 different coefficient values. So at the beginning, we initialize the weights randomly. Then we will create a linear regression model based on these values. Then we will calculate the error using the loss function. Remember, loss function can be mean absolute error, mean squared error. There are different types of loss functions. Then according to our terminate condition, if the condition is true, then we will terminate the process. But if it is not true, then we will update the weights using the learning rate and some differential operations. I will elaborate this part. I will explain these updating parts. But the main idea is, again, create a linear regression model with updated weights, calculate the error, and if it is minimum, if it is satisfying, terminate the flow. If it is not minimum, if the error is too high, then again update the weights according to the learning rate and some differential operations. There are a couple of techniques to updating the weights, but I will show the major ones. I will show the fundamental of updating weights. And updating weights will be something like that. At the beginning, We will initialize the model with random values, so the model will be wrong, too wrong, but then it will converge to the optimal point, the best for the minimum error. But how? Okay. Remember, we will update these values, these weights, to minimize the error. Okay, we will use gradient descent algorithm to update the weights. And now I will show what is it. This is our equation. This is a major equation to update the values. This equation is only for beta 1, but actually it's same for all. For the beta 1, for the new value, we will use older value. And we will extract some value from the older value based on the learning rate and some partial differential operation. And alpha is the learning rate. This is the older value. This is the new value. And this part is the partial derivative of L. L means loss function with respect to the beta 1. Remember, this equation is for beta 1. So if you want to calculate the new beta 2 value, then you can just write beta 2 new value, beta 2. And here alpha will be same for all the learning rate. But here we will calculate the partial derivative of loss function with respect to the beta 2. Okay, let's look at a graph to explain it better. Here, this is our iterations, this is the loss function's results. Orange point represents the result of loss function for each iteration. For the first one, as you see, our loss function's result is too high, which means the error is too high. We will use the learning rate, the alpha, and the partial derivative of L with respect to the beta 1, for example, for the beta 1. Then we will extract this value from the older value to find the new value. Then we will calculate the loss function for the new value. And this is the new loss function result, okay? And as you see, according to the slope, steps will be different. When slope decreases, the step size will be also small. And learning rate directly affects this step size, as you see here. Each step size depends on the learning rate and also, of course, the error itself, because we are calculating the partial derivative of loss function with respect to that specific weight. Here the question, what if the learning rate is too small? If the learning rate is too small, then step size will be small, right? Because there's a multiplication operation here. And if the learning rate and the step size is too small, then the learning process will be too long. Learning time will be too long. But also if it is too high, the learning rate, if it is too high, then the step size also can be too big and the gradient can overshoot the minimum point. So we should find the best and optimal value for the learning rate. Usually small values like 0.005 or 0.001 can be better at the beginning. But of course you should find the optimal value with experiments, because it depends on your project, it depends on your model. Okay, now we saw the fundamentals of linear regression, we saw the model, we saw the equations. Now we will see how to evaluate the linear regression model.